Hi everyone. In this video, I'm going to go over the equations of motion, and specifically some of the applications of these equations of motion. So far we've considered two different scenarios here. So we've considered uniform motion. So that's motion that travels at a constant speed in a straight line. So for example, say you were traveling on the highway at a constant speed of 100 kilometers an hour. This would be an example of uniform motion. Uniform acceleration, on the other hand, is if the acceleration is constant. So in other words, the acceleration stays the same. Let's look at an example here. So Aaliyah loves to rollerblade. If she bladed for 2 hours at a speed of 12 kilometers an hour, how far would she travel? So first, we're going to want to figure out if this is uniform motion or uniform acceleration. So from this problem, we can see she's traveling at a speed of 12 kilometers an hour, right? She's traveling at a constant speed of 12 kilometers an hour. So this tells me we're looking at uniform motion. And since we're looking at uniform motion, we can use the uniform motion equation here to find the distance Aaliyah travels. So we can see from our uniform motion equation, the distance is equal to speed times time. So let's use that formula now to figure out how far Aaliyah is going to travel. So we know she's traveling at 12 kilometers an hour. For 2 hours. So we're just going to multiply that together to figure out what distance Aaliyah travels. So 12 times 2, that gives 24 kilometers. So we know then Aaliyah is going to travel 24 kilometers. Let's look at another example here. This one's a little bit longer. So a snowboarder loses his board and it slides downhill away from him. A friend retrieves the snowboard from a snowbank 15 meters down the hill. The friend then tries to slide the dropped snowboard back to the boardless friend with an initial velocity of 12 meters per second uphill. Unfortunately, the snowboard slows uniformly and stops 3.0 meters short of the intended recipient and then begins to slide back down. So in part A, we want to find the acceleration of the snowboard as it slides uphill. Okay, and here's a picture of the situation, what's going on. So the friend is sliding the snowboard up to his his other friend here. And to help us out here, we're going to define a positive and negative direction, just to help us out. So we're going to define the positive direction as being uphill and the negative direction as being downhill. The reason we want to define a positive and negative direction is because we'll need that when we're plugging these values into our equations, our motion equation. Now, this one more thing we know here, and we know we're looking at uniform acceleration. So if you'll notice from the problem, it says the snowboard slows uniformly. Since the problem tells us the snowboard slows uniformly, right? The acceleration has to be constant. We're dealing with uniform acceleration. So we can use one of our uniform acceleration equations here to figure out which equation we have to use. Let's just write down what are we given here. So the first thing we know is we know the displacement. We know the displacement of the snowboard. Right, so it says the friend tries to slide the snowboard up a snowbank to his friend that's 15 meters away. But the snowboard stops 3 meters short. Right, so he wanted to slide it up 15 meters, but it stops 3 meters short. So in total, it's going to travel 15 minus 3, so 12 meters up the hill. The initial velocity is 12 meters per second. Right, and we'd say the initial velocity here, we're going to say it's positive, right? Because it's going up the hill, right? The displacement here is positive. The initial velocity is positive because this is going up the hill. And remember, we defined that direction to be positive. We also know the final velocity. All right, so you can imagine. So the snowboard is going to go up the hill and then stop. So once the snowboard stops, it's going to have a velocity of 0 meters per second. So that's going to be the final velocity. And here we're looking for the acceleration. So that's what we don't know. So looking at this, you'll notice we're not given the time here anywhere, and we're not trying to find it. Right? So we can use that to help us figure out which equation we should use here. We're not given the time, we're not trying to find it out. So the only equation here that doesn't use the time is the time-independent formula here. So we can use one of these equations here to figure out the acceleration. So let's use it. Let's plug it into our time-independent formula to figure out what the acceleration has to be. Just going to plug everything in, right? The final speed is 0. The initial speed is 12. The displacement is 12 meters up the hill. 0 squared, that's just 0. Okay, 12 squared, that's 144. 0 minus 144 is negative 144. 2 times 12 is 24. And we want to divide that to get the acceleration. And negative 6. And here, the units are going to be meters per second squared. And there you go. And you'll notice here we have a negative in front of the acceleration. And again, all that negative sign means is that the snowboard is accelerating down the hill. Part B. What's the velocity of the snowboard after 2.8 seconds? So again here, we're going to want to write down what are we given. So again, we know the time here. We know the time is 2.8 seconds. We know the initial velocity is 12 meters per second up the hill. Yeah, so we know the velocity is going to be 12 meters per second up the hill. What else do we know? We know the acceleration from part A is going to be 6 meters per second. And we're trying to find the final velocity. So you'll notice here in this situation, the final velocity is different. Right? The final velocity is not going to be the same. It's going to be different. Right? Because we're looking at different situations here. In the first case, the final velocity, that was the velocity when the snowboard reached the top of the hill. The velocity after 2.8 seconds is going to be different. We don't know what that is. That's what we're trying to find here. So let's take a look here. So here I can tell I'm not given the displacement, and I'm not trying to find it. So if we look back at our motion equations, we're going to want to use the displacement independent formula, because this is the only one that does not include displacement. So let's use our displacement independent formula to find the final velocity. Just going to plug everything in. So we have v1, that's 12. The acceleration, that's -6. The time is 2.8 seconds. I don't need the units here, so... Right, the time is 2.8 seconds. And if we just plug that into our calculator, we'll get -4.8 meters per second. And remember, the negative, all that tells us is after 2.8 seconds, the snowboard is going to be traveling downhill at 4.8 meters per second. Because negative is in the downhill direction. That's how we defined it. Okay, last question here. The time it takes for the snowboard to return to the friend who threw it. Okay, how can we figure that out? Well, when the snowboard returns to the friend who threw it, the displacement is going to be 0. Right? Because the snowboard returned back to the person who threw it. So we're going to know the displacement is going to be 0 meters. Again, we know the initial velocity here is going to be 12 meters per second. We know the acceleration from part A is going to be -6 meters per second squared. And we want to find how long did this take. So here, you'll notice we're not given the final velocity, and we're not trying to find it. So we're going to want to use the final velocity independent formula, which is and now let's plug everything in. So we know the displacement is going to be 0. We know the initial velocity is 12. We know the acceleration, that's -6. And we're trying to find the time. Okay, half of -6, that's -3. Okay, now we just want to solve this equation for t. Well, something you'll notice here is we can common factor this out. Right? We can common factor this equation to help us figure out the solution. So here, I'll notice, okay, 3 is a common factor because 3 goes into both 3 and 12. Delta t is also a common factor because delta t goes into both delta t and delta t squared. So we're just going to common factor that out. Okay, now we want to find, okay, what's the time? Okay, what does the time have to be to make this whole expression equal to 0? Well, there's two possible solutions. One of them is if the time is just equal to 0 seconds. And the other one is if the time is equal to 4 seconds. Right? Because if you put t is equal to 4, this will make this equal to 0. So we know that's another possible solution. Well, 0 seconds. 0 seconds is the time the friend threw the snowboard up. So really, the answer we're interested in here is this one right here. So this tells us it's going to take 4 seconds for the snowboard to return to the friend who threw it.